Yeah, this is one of these questions from 11.1 where find a unit vector parallel to and perpendicular to this function at this point. And we saw this, we did some homework with this, and then we had a quiz question. I just wanted to do it again. I mean, what do you need to do? Do you guys know? Do you remember now?
Yeah, you take the derivative.
We need a derivative because if we're going to be parallel or perpendicular to a graph, we need to be parallel or perpendicular to the tangent line. So I need the derivative. I need to know the slope of the tangent line at that point, right? And then I can work off that. So that's what I need. I need the slope of the tangent line at that point. So this gets to do a little calculus. Again, in this chapter, we haven't got to do derivatives. Anyway, this is a good derivative because it does make me do a product rule. Do you guys agree?
Yeah.
A little product rule would be the derivative of the first, 2x, multiplied by the second, sine of 2x, plus, write down the first, x squared, and now take the derivative of the sine of 2x, which would be the cosine of 2x. Oh, but the chain rule says when you do that derivative, the chain rule spits out a 2. So it's a multiplied 2. I'll just put it out front here, or out in front of that. Yeah, good. You guys okay? Little product rule. And then if I evaluate this at pi, it won't be pretty. That's why I was struggling trying to come up with some place to evaluate this. But at pi, well, one thing that happens is you get the sine of 2 pi. Let's see, the sine of 2 pi is 0. You sine it, so that whole term goes to 0. 0. And then the cosine of 2 pi is a 1. But I'm also plugging a pi in there. Cosine of 2 pi is a 1? Yeah, and I'm plugging a pi in there, so this is kind of funny looking, but I guess that's my slope. My slope is 2 pi squared. And if I want to be exact, that's my slope. If I want to be approximate, I punch it in my calculator, and it's roughly 19, 18, something like that. Yes, sir?
So my calculator gave me a weird answer. I take it 2 pi is 360 degrees, and my calculator's in the wrong mode.
Perhaps, right. If you're asking your calculator to help you with the sine of 2 pi, and you're in degree mode, you'll get some weird answers, right? If you ask your calculator to do the cosine of 2 pi and you're in degree mode, right, that'll be an issue, right? Because the sine of 2 pi was 0 and the cosine of 2 pi was 1. It was that simple. I still got a little weirdness because I got this pi. 2 pi squared, that's my slope. Anyway, if I want to keep it exact, I'll just leave it like that. And then it's important to think of slope as a rise over run, as a ratio. So I'm going to think of it as 2 pi squared over 1. And then to me the key is this. You also think of slope as a change in y over change in x. So now when you go to write a vector, I think of a vector as sort of a 2D vector like this, as sort of a change in y and a change in x. Oops, wait a minute. A change in x and a change in y, right? And so I think my vector should be 1, 2 pi squared. And I've done a great job of finding a parallel vector. What I didn't do, though, yet, is make it a unit vector. They asked for a unit vector. I've tried to warn you, though, when the question asks for a unit vector, my advice is to ignore the unit vector, do the work, get a vector, and then unitize it later. If you try to make it a unit vector during the process, it just doesn't work, and you get stuck. So just get yourself a vector. You don't care what the length is. You can always make it a unit vector by dividing by his own magnitude. What is his magnitude? And you don't have to simplify it. You can just tell me what it is. It's what is his magnitude?
Square root of 1 squared plus 2 pi squared squared.
That's right. So I think it's that. 1 plus 4 pi to the 4th if you squared to 2 pi squared, right? And again, if you're leaving it all exact, you're done. And if you wanted the perpendicular vector, what would you do? Go ahead, what were you going to say?
You would like flip the slope and negate it?
That's true. I mean, so you could go over here and think about a perpendicular slope is the negative reciprocal, and you could think that through, but the truth is, perpendicular to him, maybe we learned about in our little shortcut, to be perpendicular, we know that the dot product will be 0, and kind of what that amounted to was an idea of flipping and negating. I had this idea in 2 dimensions. If you want a perpendicular vector, you flip, well, flip's not the word, I mean, whatever. You switch their places and negate one of them. Doesn't matter which one, negate that one. And you've just made a perpendicular vector. And now he's a unit vector. You guys okay? Yeah. I didn't need to draw all this out. I mean, it's kind of might be cool to see a picture of this guy, but whatever he is, he's some weird function. At that point, we found the slope of the tangent line, which led me to these 2 vectors. Not too difficult, really. But the key is getting a derivative. And then I guess maybe, you know, you haven't done a product rule in 10 years. Could get you, but I don't know. That's pretty good. I don't know. Sometimes I don't do a great job. I mean, I can sit here and think of questions off the top of my head. I guess I do a decent job of that. But it does help if you have questions. Anybody thought of anything yet? Right? Yeah.
On that one,
Yeah.
I was working through it while you were doing it.
Yeah.
And I take it as you pointed out about the slope, you can literally go from slope to vector instead of going through the long process I did on Friday.
Huh.
In the quiz.
I'm not sure what you might have done on Friday, but you're right. Once you have the slope, I think of slope as a change in y and a change in x. Oh, it's a ratio. You know, and a vector is a change in x and a change in y, not a ratio, but a component. So there's a connection between a vector and a slope. It's rather strange, and when I study vectors, I hardly use the word slope, but if we have a slope that has a rise and a run, I can make a vector with that rise and that run. All right, yeah. So, it's just, you know, if you're just kind of not thinking, you know, this is the numerator, this is the denominator, this is first, this is second. When you go write this, you put him first and him second, you're wrong, you know. Anyway, you got to have, it's y over x. So you got to have the x and then the y. You know, think it through. I have. I don't know. This reminds me of a question I had on a test once. So if here's a vector. So anyway, so there's more than one answer, but I need I want something parallel to u. And let me give you another vector. So there's u, here's v. There's a vector v. So anyway, this thing's asking for something parallel to u. Just please. B wants something perpendicular to v. And maybe I'll use the word orthogonal. I think that's more appropriate, but perpendicular or orthogonal, either way, same word, same meaning. What's part C want? Part C wants perpendicular to both u and v. Maybe this one should say perpendicular to v, but not u. one wants it perpendicular to both you and me. Anyway, got any ideas? Are these easy questions? Are these hard questions? Do you know how to do these? What about the first one? Can you come up with something?
Negative 16, 4.
All right, I like that. What did he do? He multiplied by any scalar he wanted. He picked an easy scalar like 2, and he said 6, negative 16, 4. It's just 2 times u is parallel to u, right? Scalar multiple. Yep. Yeah, that's easy. So there's millions of these answers. There's not, yeah. What about this? I had fun playing this game once. How do you come up with something perpendicular to v?
Since there's 3, it's hard to switch and negate.
That's right. So you don't really do the switch and negate, maybe. But that's good. You were thinking of that. And maybe you could do some version of that. Again, there's millions of answers to this, too. There's definitely more than one right answer, infinite answers. Perpendicular to v. I mean, the key is the dot product should be 0. That's how you get 2 vectors are perpendicular when their dot product is 0. So you can almost kind of make something up. If you see these numbers, you could I mean, I don't know. What if these numbers aren't the prettiest numbers here.
Could you do 0, 0, 0?
What'd you say?
0, 0, 0.
You know, yeah, I might not like that. I might want, maybe I'll have to paraphrase my question. I might have to add this like a lawyer, you know. I want what we call non-trivial answers, please. That 0, 0, 0 is a vector, and it would almost be the answer to all this.
That's true.
But let's not go with that guy. Yeah, let's exclude him. Yeah, he's not much of a vector. And anyway, you call that kind of maybe the trivial answer, 0, 0, 0. So non-trivial answers, please. You know, you said, here was one idea. You said you can't really switch and negate. You know, actually you can if you threw in a 0. So like if I threw a 0 in the middle there, I could switch and negate the other 2. So I could switch and negate the other 2. Now wait a minute, switching the other 2, negating one of them, that's how you do it. And does that work? That's negative 20 and 20 and 0. That's, yeah, that works. What do you want to say?
Could you find a parallel vector to v and then cross product them?
What am I looking for? Now wait a minute. I'm looking for a perpendicular vector to v. So parallel to v.
I don't think you can cross product because if they're parallel, they're not touching. So you can't.
Yeah, you know, I don't know if I probably never said this real clearly, but if you could stumble into it if you do some homework sometimes, you could stumble into it. If you ever do try to cross product 2 parallel vectors, you can do it. But when they're parallel, you can watch how it happens. You get 0, 0, 0. And you get the 0 vector when you cross product 2 parallel vectors. It doesn't. Actually, hang on a second. Let's just watch it happen. It's because of this multiple thing. Watch, right? Look what I did. I just multiplied by 2, right? So now if you did it, look, you get negative 70 minus negative 70. Look, you get 40, negative 40 minus a negative 40. You get 56 and 56. I mean, it works. You get 0, 0, 0. Anyway, so whenever you do a cross product for purposes like especially up in 11.5 and so forth, you know, we always said you need 2 vectors and then you do the cross product, but they really had to be non-parallel vectors, right? So when we had to find 2 vectors in the plane in order to do the cross product, we could never find, if we found 2 parallel vectors, that ain't 2 vectors. That's really the same damn vector. Right? Not exactly, but kind of. So go ahead.
Could we find an arbitrary vector that's not parallel to u or v, and then cross product that and v?
Oh, and then, yeah, you can. You don't have to work that hard. First of all, this works, right? But what you said would work. I like this thing. I like this algebraic approach. Watch this. where you just say, okay, here's an answer. 1, 1, I don't know, A. And then I want the dot product to be 0, right? So then I do the dot product. That's a 4 plus a 7 plus a negative 5a, and it has to be 0. You with me? And then I can algebraically find a, and then I got an answer. That's kind of that's one approach. Throw any numbers you want in there. You can always find the third number. Throw any 2 in there and do some algebra to get the third one, based on the concept that the dot product has to be 0. Right. What is this? Negative 12. I mean negative 11. 11 fifths. So A would be 11 fifths. You can't really do those in your head, but you can do them like that. Yeah. So now we found one, or that one, or there's a lot, right? But that's a cool approach, right? This little algebraic approach. Hey, what about the last one then? You know what to do the last one?
That's the cross product.
That's the cross product. You're right. Right. To be perpendicular to both, we need the cross product. Should we even bother?
Nah.
I mean, when I do a cross, I can't really do these cross products in my head. I gotta do them. I gotta write them out. I don't know what you've been doing, but I mean, I don't really advise doing anything in your head too much. I write it all out. I'm just gonna, but then I can do it quickly, right? Because then I do this part in my head. I do 40 minus 14, 26. I do negative 15 minus 8. Negative 23, but it's positive 22. 21 minus a negative 32. 21 minus a negative 32 is 53. And we're finished, I guess. Yeah. So, anyway, there's some easy stuff on this test. I mean, it's all kind of easy. But sometimes I've had some bad test scores on this chapter 11. I mean, students, maybe they do think it's easy and they haven't really practiced it hard enough. But again, last thing I was doing Monday was practicing a lot of different 11.5 kind of questions. How to get the equation of the plane in different scenarios.
Do we have to know the midpoint formula?
You know,
Or distance?
I guess you kind of should, perhaps. I mean, one classic question back there in 11.2 about spheres would be, find the equation of a sphere. Find the equation of a sphere. And so this I might have something like this. I tend to, I might word it a little different, but then it has, and then they do this. They do this. It has 5, 1, negative 8, and 4, 3, 0 as endpoints of a diameter. So this is kind of a classic question. And then in this case, I do need to know how to find the midpoint. Don't you agree? Because if they just gave me 2 endpoints of a diameter, I need to find the center. And so I need the midpoint. And I never talked about the midpoint formula like it was some formula. I guess I always assume the midpoint formula is common sense and you already know it. But maybe that's not true. Do you know how to find the midpoint? I mean, you look up the formula, but
Is it just x?
It's kind of an averaging thing. You add your x's, divide by 2. You add your y's, divide by 2. You add your z's, divide by 2. It's like averaging to find the midpoint of 2 points. Yeah. So using the midpoint formula or sort of common sense, the center would be 9/2, I think. Do you agree?
Yeah.
You actually add them. You don't subtract them. I mean, we do some subtraction of points in this class, but I'm adding and dividing by 2 to get the midpoint, right? 4 divided by 2 is 4 divided by 2 is 2. And -8 divided by 2, when I add those, that's -8 divided by 2 is, yeah. So now I got the center. I'm trying to get the equation of the sphere, and so I need the center and I need a radius. And now I do need a distance formula, right? Which, right, I do need. Again, I kind of thought of that one as, I think of that formula as kind of common sense, but like, you know, it's been in your soul since 7th grade, but you know, maybe that's not true. But anyway, let's see, what could I do? For the distance formula, you know, you got 2 options. Now that you got your center, you can do the radius. If you do this distance, that's a radius. Or this distance, that's a radius. If you choose to do this distance, when you're finished, please divide by 2, because that's the diameter. You got those 3 options, right? I think I'll do that diameter. And you know, the distance formula is the square root of, subtract your x's, 5 minus 4 squared. 1 minus 3 squared, that's a -2 squared. Subtract your x's squared, subtract your y's squared, subtract your z's squared, add them all up and take the square root. Subtract your z's, -8 squared. 64, or I could have wrote -8 squared. Cool, this is my distance, and it's my diameter. And it's 1 plus 4 plus 64. Hey, that's pretty cool. That's 69. The square root of 69 is, I don't know. I was thinking of the square root of 169. You know what that is? 13, yeah. I was about to say 13. This is not, yeah, this is just the square root of 69. 4 plus 64 plus 1? Yeah, okay.
8.
Yeah, that's the diameter. 8 point something. Divide the radius is the square root of 69 divided by 2.
And then we square it.
And you guys okay?
Yeah.
So now I got a center and a radius. Can you write the equation of a sphere? Sometimes students mess this up. They don't really, I don't know, you know, we didn't focus a lot on it, but we should know that it's x minus the 9/2 squared. Some people leave off the squared, that's bad. It's y minus 2 squared, that's my center. It's z plus 4 squared. And then it equals this radius squared. And that radius squared would be 69/4, I guess. You guys all right with that? That's a decent question. That was... You know, I asked you the other day in class, since we're on this little topic of spheres, and it could, you know, I asked you this question the other day in class. I made a cube here. I said I had a cube sitting here of radius, of sides 1. It was a 1 by 1 by 1 cube. And I asked you for the sphere that circumscribed it. Or then I also thought about maybe inscribing the sphere. So that was a good question. And that made me sort of think about a sphere that circumscribes this. You know, that means barely touches these corners, but basically the center of the sphere will be the center of the cube. And what's the center of the cube if it goes out 1, over 1, and up 1? The center is if the cube is a 1 by 1 by 1 cube, you go out 1, over 1, up 1 to get to this end, and you started here at 0, 0, 0. How do you get to the center?
Out half, over half.
Up a half, I mean out a half, over a half, and up a half. You're right. So the center is a half, half, half. I mean, anyway, I was thinking of it differently. I could have thought of it as that's an end point of your diameter. That's an end point of your diameter. Please find the midpoint. I didn't say it like that, but if you have a 1 by 1 by 1 cube, the midpoint, or the center of the cube, or the center of the sphere that is around that cube is a 1 half, 1 half, 1 half. Right? Then how do you get the radius? How do you get the radius now?
Distance between the origin and the...
Sure, or to any of these corners from that center, which is hard to draw this, I'm sorry, but from that center to any of these corners, but you're darn right, that corner would be a good one, or that corner would be, I mean, right, that distance right there would be a radius. From the center to that corner, if the sphere is touching the corners, right, if the sphere is touching those corners, then that would be a radius from the center out to one of these corners. So there you go, right.
If it was inscribed.
If it was inscribed, that's different. You're right. That would be different. Then the sphere is sort of touching these faces. So then what would it be its radius?
Distance between
See, then it's
5.51, I think.
I mean, now if I drew a box around the sphere, the box touches the sphere in the center of those faces, right? Now I know that that distance is
0.5.
Yeah, 0.5. If the sphere was inscribed in the box, that's a little easier. It's not touching the corners, it's touching the face, it's kind of easy. Right. All right, so we're speculating on sphere questions. That's cool, that's fine. So his question started was, should I know the midpoint formula and the distance formula? I guess maybe you should, but yeah. But we see how, I don't know how it plays out. And if you do need it, it's probably just for one idea, one question. Any other good questions? Well, let's do something else then, maybe. We've got a little shorter class today. We don't have too much longer here. I want to show you, I got 10 minutes or so. I might show you something different. So this is kind of more for next week, but let's do it anyway here. So I'm saying, if we go back to 11.6, we started sketching some things. Now, what about this thing? Y squared plus z squared equals 4. Could you say anything about that? I don't know what you remember from the other day. We did something similar but different.
Infinite cylinder stretching in the x direction with a radius of 2 in the YZ plane.
Okay, good job. He said it. Do you guys agree with them?
Yeah.
Yeah, good. I mean, when you look at that, the first thing I think you should say, your brain should say maybe is, hey, that looks like a circle. Radius 2, centered at the origin, circle. But wait a minute, it's got that missing x, so it must be a circle in the YZ plane. And because it's got the missing x, it must be running out infinitely in the x direction. And therefore, right, it's not really a circle. In 3D, it's called a cylinder, right? And you're exactly right. It's in the YZ plane, centered at the origin, radius 2, circle. It's kind of hard to draw, maybe not. But then again, because of the missing x, this thing is a cylinder running infinitely back into the board and infinitely out at me here. What I try to do is draw a parallel circle out there somewhere, and it sort of looks like a cylinder surrounding the x-axis. Yeah. Generated sort of by this circle in the YZ plane, radius 2. Yeah, good. What we said is anybody with a missing variable is called a cylindrical surface. They're not all cylinders, but they're called a cylindrical surface. Here's another one. Here's another one. Ooh, this is another one. It's time to substitute. Time out. Let me switch this to an X. Yeah, that's weird. All right, hang on. That is kind of weird. In 2D, you know, it's in the XY plane. But then it's got this missing Z, so whatever it is, it runs infinitely in the Z direction. I'd like to try to draw it. Here's what I tried to teach you last week about drawing this. I tried to say, that for just a minute, my brain works like this. I say, okay, this is this E function. Now, when I study E functions and I remember E functions, I remember them like this: y equals e to the x, and I know what it looks like. On the y-axis and the x-axis, it looks like this. Now, hold on a second. This is not y equals e to the x. The variables are switched. It's x equals e to the y, which I don't feel too familiar with. You know, if you wanted to solve for y, what would you do? If you wanted to solve for y, what?
ln.
You would ln both sides. So then you'd have y equals the ln of x. Oh, that's really what this is. This is y equals the ln of x, which is not him. Y equals the ln of x is actually this guy. Anyway, I can call him y equals the ln of x, or I could call him x equals e to the y. I mean, that's what he is. He's not y equals e to the x. He's x equals e to the y. So there he is. He's kind of the e function, yeah, there he is. And he dives toward this like an asymptote. I wonder if I can get that onto this picture. In the XY plane, oh my God. In the XY plane, what am I doing? I'm diving toward the negative y-axis. I cross the x-axis at 1. I come out here into the first octave. Oh, and I dive toward the negative y-axis. Look, I think this is accurate. This is that XY plane turned, flattened, and put here. Now, run him infinitely parallel to the z-axis in the z direction. Well, I do that by doing this. I run these sort of parallel lines up here. And I try to kind of connect those with a parallel curve that I kind of parallel to what I drew down there. Damn, that ain't bad. It's an infinite well, that ain't too great. It's an infinite exponential sheet. It's coming out at me, man. All this stuff that comes out at me is hard to draw. But it gets weird when it comes out toward me. So we studied these concepts a little bit. I mean, we laid out, we got introduced to them, and I'm reminding you of them. But I want to add this to the conversation, and I got that 5 minutes left, but I want to talk about these, because this is the other big topic in 11.6. There's 6 of these famous quadric surfaces, but I don't really like to study all 6 of them. There's only 4 I like, and so the first one is an ellipsoid. It's a 3D ellipse, and its equation looks like this. I'll tell you what, I'm going to make up one with some numbers. Your book does a good job of sort of outlining it in general. Now, I don't know how much you remember about ellipses, but this is sort of standard form of an ellipse in 3D. This is sort of standard form. Back in 2D, you know, this was standard form of an ellipse, kind of. This one is centered at the origin, though. But with the third one there it is. So it's a 3D ellipsoid. I'm going to try to draw it for you. You ready? This is going to be tricky. It's centered at the origin. Again, I don't really know how much you remember about ellipses. It's good to know a little bit about these things. What I remember is that this is called an a squared, a b squared, and a c squared. And that a squared is 4, which makes a 2. And that means in the x direction from the center, which is 0, 0, 0, thank God, we come out 2 and back 2. In the y direction, I think I'll go over 3 and back 3. Now let's pause there and draw and connect those guys. That's sort of my elliptic equator. I mean, I've got a 3D ellipsoid sitting here, but that's sort of its, what you call its trace in the xy plane. What about in the z direction? In the z direction, it's going to hit at 4 and negative 4. Now watch this. I can trace this in the xz plane. That's me connecting these dots. Are you following this? That's the trace in the xz plane. Are you following me?
Yeah.
And now watch, I'll do the trace in the yz plane. That'll connect the 3's with the 4's. And that ain't a bad picture. Looks almost like a sphere, but it's not supposed to be a sphere. It does have these different radii. It sort of has 3 radii. That's actually a false statement, but sort of has 3 radii. A radius of 2 in the x direction, a radius of 3 in the y direction, a radius of 4 in the z direction. I could have made that 4 bigger. It's not quite accurate, I guess. But that ain't a bad picture. I hate to erase that. These are all outlined. Let me just point something to you. You don't need to get your book out, but if later, if you're studying these, here they are. These 6 quadric surfaces are outlined in 11.6 on these 2 pages. So they're outlined well. They talk about them. You can read about them. The next 2, I started with the ellipsoid. The next 2 I'm going to skip. They're kind of cool. It's a hyperboloid of 1 sheet and a hyperboloid of 2 sheets. They look kind of cool, but I just got enough stuff to memorize, so I'm not going to do those. I will say this. When you change one of these plus signs to a minus sign, you get the hyperboloid of 1 sheet. When you change 2 of them to minus signs, and keeping one of them positive and change 2 of them to minus signs, then it's the hyperboloid of 2 sheets. Anyway, I'm going to skip both of those, but it's interesting that their equations are practically this guy. Just real subtle differences to the equations. Let's move on. The next one I like is the cone. Now in general, I call it a cone. In general, it is an elliptic cone because it doesn't have to be circular. So it could be elliptical. And its equation in general is a z squared equals an x squared plus a y squared. Now wait a minute. The truth is, you could have coefficients. You could have over an a squared, over a b squared. That's how the book presents it. That is how the book sort of presents it. In fact, they present it differently. I like what I wrote. The book wrote this: x squared over a squared minus plus y squared over b squared minus z squared over c squared equals 0. Can you see how that can get turned into mine? Well, if my a, b, and c were all 1s, then can you see how that is mine? Yeah. But it's a cone, and it's a double cone, really. Here it is. It's a double cone. Listen, my little simple one here that we can talk about them in general, but I got a specific one here. My specific cone is not elliptical. It is circular, but in general, depending on the A's, B's, and C's, it could be elliptical. These could be elliptical cross sections, but my particular one here is circular. And another little notice on mine is because of all the 1s, and 1s, it kind of goes up 1 and over 1, up 1 and over 1 here, I think. So this is a beautiful 45-degree angle cone, actually, is what this guy is. He's sitting there perfectly 45-degree angle there. But again, depending on the numbers, it could be skinnier or wider or more elliptical and less elliptical. But it is really kind of a double cone, above and below the z-axis. Hey, I suppose if this is positive, and this is negative, it's doing this z-axis thing. Listen, what if those two are positive and he's negative? I think it's a double cone in the x-axis direction. So these things can be, yeah. Listen, there's only 2 more. I've kind of slipped into overtime, but not too much. Here's this guy's real closely related. He's a paraboloid. He's closely related to the cone, and again, yeah, technically he's called an elliptic paraboloid because he could be elliptical. I tend to just watch this. I tend to go with this equation right here, which is kind of the easiest, most basic paraboloid. But it can be different coefficients. We could put a squareds and b squareds in there. We could change it up a little bit. But paraboloids are nice. Look at this. We study these a lot. We work with these a lot. This sits at the origin and it opens up in both directions like a parabola. Like I said, it's got a circular top in my specific case, but in general it could have elliptical cross sections. And by the way, I sort of top it off here just to show you the 3D picture. It is infinite. It actually is infinite, So is this cone, But it's cool. It's like a bowl, it's got not a great bowl. If you set it down on your, if you had a bowl like this, it would probably spill, right? Because it doesn't have a very flat bottom. It's good. Unless you balanced it perfectly.
It's kind of like what we did in Calc 2 when we did the shell method.
Well, in Cal 2, when you did the shell method and the disk method, you were taking 2D shapes, spinning them around an x-axis and creating a 3D shape. And finding the volume of it with this cool disk method and stuff. You're right. We're studying 3D shapes now. This particular one and this particular one, you're sort of right, could be generated from a 2D shape revolved around an axis. Right, because of the symmetry of the shape. Anyway, 1, 2, 3, 4. Okay, one more for you here. One more and then we'll quit here. The last one is called z equals x squared minus y squared. Again, just my simple example. In general, it could have a's and b's in there. And this one is called an elliptic. What the hell is this going to call? An elliptic, the last one. Oh, no, it's not. I'm sorry. It's hyperbolic paraboloid. I never remember its name because, and I don't know if I care if you remember its name here. I like the other names. Because what I do is I got a different name for it. It's a saddle. We call it a saddle. And why do we call it a saddle? Because when we draw it, oh boy, the picture, these are hard to draw. The pictures in the book are good. It's kind of like a parabola one way with perpendicular parabolas hanging off of it. Jesus. These are supposed to be perpendicular to it. That's horrible looking. Listen, but it's like this. Here. It's like a horse. That's why we call it a saddle. When you're sitting on a horse, the horse has kind of a swayed back. You know, the neck is here and his butt kind of rises up behind me. Right, the horse kind of has a swayed back, like a parabolic shaped back, and then you're hanging off, your legs are hanging off the side, so you've got these parabolas hanging off the side. Yeehaw! And that place right where your butt sits is called a saddle point. Later on we'll discuss that saddle point. It's kind of a level place, but it's not really a max or a min. You can look at it one way and maybe think of it as a max, but if you look at it the other way, it looks like a min. It's sort of neither a max or a min. It's a saddle point. So these are interesting surfaces. Similar to again, their equations are very subtly different. All these equations involve x squareds and y squareds and z squareds, except these don't have a z squared, I guess. They have plus and minus signs, and they have, they're just subtle differences in these equations, and they all fall into this category of quadric surfaces. So I'd like you to know these four. What I'll do for 11-6 is I'll come up with some kind of a sketching assignment. You could try some sketching in the homework, but you could do that and do my sketching assignment. But we'll do a little of that next week, and we'll dive into chapter 12 on Monday. But we'll stop today, and we'll take a test Friday. I'll see you at 10:30.